So we've been talking a lot about conditional probability, right? And we'll keep talking about conditional stuff for the entire semester. So the plan for today is do one more famous important example of thinking conditionally, and then we'll start on random variables. And if I had to name the two most important ideas for the entire semester, I think it would be conditioning and random variables and their distributions. And so I said before, conditioning is the soul of statistics. And I like to watch the Colbert Report, and my favorite thing on that show, he hasn't done it as much as I'd like, but my favorite thing on the Colbert Report is when he asked the guest, like, explain quantum mechanics at 5 words or less, and or explain how the mind works. He asked Steven Pinker, how does the mind work, 5 words or less. So sometimes I try to think, what's Stat 110 about in 5 words or less? That should be 5 words or fewer. Unfortunately, conditioning is the soul of statistics. I think has one too many words, conditioning. But I thought of a clever way around that. I just put a colon, conditioning, the soul of statistics. That would be one answer. What is this course about? We're going to be conditioning the entire time on different things. The second thing, these are my two answers to that question, so that's actually 10 words, but I can't decide between them. But it's okay, because I'm not actually on the show. The other one is random variables and their distributions. So that's what we're going to start on in the second half today. And then we'll be continuing doing random variables for the next few lectures, but also we'll be using them for the entire semester. And, okay. I have had one Stat 110 alumni has been on the Colbert Report, but I think only one so far, so hopefully some of you or me can be on the show someday too. But at least I've had one. Now, all right, so that's 5 words, right? Okay, good. All right, so we'll get to random variables a little bit later. I'll tell you what all that means. Right now we're still thinking about conditioning, and I want to illustrate kind of another, more about how to think about what should you condition on, how can you use it to solve problems. So here's another very, very famous, useful probability problem that's known as the gambler's ruin problem. So here's the problem. There are two gamblers. Let's just call them Gambler A and Gambler B. And they're just basically betting dollars back and forth. So they're playing a sequence of the same game over and over and over again. Okay, so two gamblers, and then they keep, successively betting $1 each time. So one of them wins $1, one of them loses $1, wins $1. Keep trading dollars back and forth. The game ends if one of the two gamblers is ever bankrupt, right? And then that's the end. But how do we know whether the game will ever end? Maybe it'll just oscillate forever. We don't yet know that. Okay, but if one player goes bankrupt, which ruin means bankruptcy in this problem. So if one of the two gamblers goes bankrupt, then the game is over, and the other player has all the money and has won the game. Okay, so there's only two players exchanging dollars back and forth. Okay, so that's the setup. So two gamblers, A and B, with the sequence. I'll call them to distinguish. I'm thinking of the word game as the entire process, and each round is one individual bet. Sequence of rounds where they bet $1 each time. Each round is independent. They're just a sequence of independent bets, $1 each time. And let's assume that P equals the probability that A wins a certain round. So for any particular round, the probability is P that A wins, and it's 1 minus P that B wins. And often in this class, we'll abbreviate 1 minus P to Q. So Q is the probability that B wins a round. P is the probability that A wins a round. Then they keep repeating that, either forever or until one of them goes broke. Okay, so that's the setup. And the problem is to find what's the probability that A wins the entire game. That is, that A wins all the money and B goes bankrupt. Okay? So that's the problem. So find the probability that A wins the entire game. So B is ruined, we would say. Or we could ask the other question, what's the probability that A gets ruined? Okay. But of course, if we can do one of those problems, we can do the other one in the same way. Okay? I'll put ruined in quotes. Ruined means bankruptcy. Now, we need to assume, what's the initial conditions, assuming that A starts with I dollars and B starts with n minus I dollars. I chose the numbers, I chose the notation this way just so that, I is just makes me think of an integer because I'm assuming integer dollars going back and forth. And I called B's initial wealth n minus I because then the total is capital N dollars. So this is a closed system, right? No money is coming in or going out. So there's basically n dollars on the table that are just, going back and forth until one player has all of the capital N dollars. That's the total amount of wealth sitting on the table, right? That's being redistributed back and forth. Okay? So that's the setup of the problem. And so this problem is important for several reasons. One is just something that it's a pretty natural problem that comes up not only in gambling, but in other cases where you have repeated trials where independently, you have some probability of success or failure, that kind of thing. Another way to think of this problem is as a random walk, which is another thing that comes up all over the place in finance, in physics, and elsewhere. So one of the most important things in this course is just being able to recognize pattern, right? So we may see problems later that, it's really a gambler's ruin. It's not phrased in terms of two gamblers, A and B, but the problem has the same structure. So an example of a problem that's exactly the same as this would be if we had a random walk that we can picture like this. Here, just draw a number line, and here's 0, and here's capital N, and here's I. I is somewhere in between. We didn't specify whether I is close to 0 or close to N or near the middle. But anyway, this is the initial starting point, and what you should, imagine that the random walks that suggest that, suppose you have like a bug or a particle that's here at position I initially, and then it moves either to the left one step or to the right one step, and it could be 50-50, but more generally, if there's probability P of going to the right and Q of going to the left, so it starts here, and then it either goes here or here, and then if it's there, well, it either goes there, back to I, or it goes to I plus 2, and keeps wandering around like that. Okay, so this will be a random walk where P equals the probability of moving right. So these kinds of processes come up a lot in a lot of different applications. And then it's not just any random walk, though. If I want it to be exactly the same problem as this, what we're really assuming is that if this particle ever lands at state 0 or state n, the game's over, right? So we would call that an absorbing state. So we have absorbing states at 0 and n. Just think of that as like a black hole or some like very sticky place where it just gets stuck there and then the game is over. It just stays there forever. So it gets trapped. So that's called an absorbing state at 0 and at n. Then the game's over. That's the same thing as here. Here, if the random walk, so think of this random walk as just tracking how much money A has. Of course, you could draw an analogous random walk for B, but we may as well just track A and then B is determined, right? So if A ever ends up here, it means A has all the money and B is bankrupt. And if A ends up here, then A is bankrupt and B has all the money. Okay, so it's the exact same problem, just in a different way to picture it, different interpretation. Okay, so that's the problem. Now let's try to solve the problem. Well, At first, this may seem like it's not so easy, right? I mean, you don't know how many rounds the game will last. You don't really know, is it possible that this would wander forever? And mathematically, that it's possible that it could just go like here to here to here to here to here to here forever. That has probability 0, okay? So it won't actually happen. But how do we know that but there are other ways where it could just wander forever and never get trapped here or trapped here. So do we know whether there's some non-zero probability that it's just going to wander forever? We don't know how many rounds there are going to be, right? So it doesn't seem like an easy problem at first. But it does have a very nice recursive structure, which is there's two cases, right? Either A wins the first round or A loses the first round. If A wins the first round, then the current state is here. But notice it's the same problem again. It's just the same problem, just starting at I plus 1 instead of I, right? And if A loses the first round, then the process is here. It's the same problem again. It's just at I minus 1 rather than I. So it has a nice structure that after one step, it's the same problem with a different initial condition. So that gives us a hint as to what to condition on. So that's the strategy. The general strategy is we have a complicated problem, we find something to condition on to make it simpler. A more specific strategy here is condition on the first step. So sometimes this is called first step analysis. There are a lot of problems where that's something that's useful to condition to. Remember we were talking about wishful thinking, like what do we wish we knew? Well, I mean, in principle, I wish that I knew, everything that's ever going to happen. I knew, but you can't condition on everything. You have to pick something to condition on that will break it up into simpler, manageable pieces. So one thing that would be useful is knowing who won the first round. Don't get too greedy. For other problems, maybe you condition on the first 2 rounds or the first 3 rounds, but don't want to condition on the entire future of the universe. Okay? So let's try conditioning on the first step. So that's called first step analysis. And then let's write down what's the equation. So we need some notation. So let P sub I equal the probability that A wins the entire game, not just a round, given that A starts with I dollars. One interesting thing about this problem is that it's actually easier to solve the more general problem than the less general problem. Like if I had given you this problem and I said, A starts with $100 and capital N is $212 or something like that, it sounds like it's easier because I gave you specific numbers, but it's actually harder because the key insight is that we're going to try to relate Pi to Pi plus 1 and Pi minus 1. So if you're thinking I has to be $100 and only thinking of that one probability, then you're not thinking of it with the right generality. Okay, so now with this idea, we can immediately just write down an equation for Pi. Pi, this is just immediate from the law of total probability. Pi equals, well, it's the probability that so this is just from the law of total probability, LOTP. We're conditioning on the first round. So if A wins the first time, then the process is here. So then the probability that A wins the game is Pi plus 1. And that happens with probability P. And on the other hand, with probability Q, A loses the first round. And if A loses the first round, then the process is here at I minus 1. It's the same problem again starting at I minus 1. So it's Pi plus 1 plus Q Pi minus 1. This is for 1 less than or equal to I less than or equal to N minus 1. And of course, we have two obvious extreme cases. P0 equals 0. That's a pretty sad case where A starts out bankrupt and nothing happens. Similarly, Pn equals 1. That's the case where B starts out bankrupt. Okay? So we have these extreme cases. These are called boundary conditions. And then for everything that's not in the boundary, we've related Pi to Pi plus 1 and Pi minus 1. Okay, so as far as we're concerned in this course, this is the most important thing about this problem, is, well, the two most important things are, one is just recognizing the problem. If we had another problem that was the same as the gambler's ruin, recognizing the structure. And the other is thinking conditionally. Write this thing down. Notice this is a recursive equation. So at this point, if you wanted to solve it either kind of tediously by hand or on a computer, computers are very good at recursion, this would be very easy because we could rewrite this for, well, we can rearrange, at least once we have, actually it's a little bit more complicated because usually with a recursion, we get the first initial conditions and then we can solve from there. Here, let's see, if we want to, we can rearrange this for pi plus 1 in terms of pi and pi minus 1. So it has this recursive flavor where terms are defined in terms of other terms. Okay, so this is called a difference equation, not to be confused with differential equation. A difference equation is the discrete analog of a differential equation. And one thing that kind of annoys me is that difference equations never get taught, as far as I know, anywhere. That's pretty sad. Like my opinion is that difference equations are at least as important as differential equations. Differential equations get taught all over the place. It's the continuous version, and difference equations just get really neglected. And the saddest thing was, I was I looked up difference equation on Google yesterday. The #1 link is Wikipedia's entry on differential equations. So that was really annoying. Does anyone know if any math class here teaches how to solve difference equations? Okay. So anyway, I mean, it seems these equations come up everywhere, right? That you can't. In fact, they're more realistic if you have generally if you have observations over time. You can only observe things in discrete time. You can never observe things in continuous time. So you get difference equations. And maybe you might approximate the difference equation using a differential equation, but it's better if you can just solve this thing. Okay, so, well, I think therefore we should solve it. Now, if you look in either book, they both solve this equation, both of the recommended books, Ross and DeGroot, they both solve this through several pages of kind of somewhat clever and somewhat tedious algebra. Okay, and I don't like tedious algebra, and I don't like clever algebra either, because then it's like, how would you come up with that? Okay, so I'm going to do it a different way, and this is actually, I mean, I could just state like the general theory of difference equations, but I think it's easier to just see what happens for this example. How would we solve it? And then actually, what I will have shown you will help you to solve any difference equation that you encounter. Anyway, at least if it's of this form where the coefficients are constants and it's what we call linear. Okay, so let's try to solve this equation. And let me see. Do I want to? I'll just rewrite the equation. Just want more room to do it. Pi equals pi plus 1 plus q pi minus 1. Let's try to solve this. We're assuming p and q are known, and we're solving for the pi's. Well, there are a lot of deep connections between difference equations and differential equations. One of the most famous methods for solving a differential equation, as you may have seen before, is to guess. So we're going to try something here. Let's guess pi equals x to the I. So we'll try to find a solution of this form. Actually, this won't work, but it will give us a hint. And actually, for any, it's not just for this one. This is like a very general good guess for whenever you have a difference equation, and it could involve higher order terms as well. Start by guessing a power, and that will tell you a lot. Okay, so let's try that. Well, we'll plug it in. X to the I equals px to the I plus 1 plus qx to the I minus 1. And well, one way to solve this is if x equals 0, but that's not an interesting solution, and that's not going to work for our boundary conditions. So let's assume x is not 0, cancel out the x. And this says that p x squared minus x plus q equals 0. Assuming that this guess is true, it must be this quadratic equation holds. Okay, well now that's just a quadratic, so we can easily solve for x. X, let's see if I remember my quadratic formula. Minus b1 plus or minus square root minus b squared minus 4ac, right? 1 minus 4pq. Okay, haven't done that in a while. 2p, there. That looks right. Okay, now this looks pretty horrible. First of all, it looks horrible. Secondly, our implications only went in this direction. So I don't, you'd have to plug that back in and see does that actually work. And I just sort of said it doesn't work. Okay, so it kind of looks like we reached a dead end. But let's try to push this a little bit further. First of all, this is not as ugly as it looks. Because remember, q is 1 minus p. So 1 minus 4pq equals 1 minus 4p 1 minus p equals 4p squared minus 4p plus 1. Well, we're kind of lucky here. This is a beautiful problem. It happens to be, I wouldn't have chosen an ugly one. It looks ugly at first, but actually it's a beautiful problem. That's just 2p minus 1 squared. So that's actually really nice because we're taking the square root of 2p minus 1 squared. So actually this is very simple. So actually this is just equal to one of two things. Take away the square. Technically there's an absolute value, but it's plus or minus anyway, so we can ignore that. If I take 1 plus 2p minus 1, the 1's cancel. 2p over 2p is 1. So this is equal to 1 in that case. The other case is where we would have 2 minus 2p, right? Just simplifying this. 2 minus 2p divided by 2p. Well, of course, the 2's cancel, so that's 1 minus p over p, which is q over p. So actually the possibilities are just 1 and q over p. So, okay, now if you plug that back in, it doesn't actually work. Well, actually, it sort of does. I should clarify here, I didn't rewrite the boundary conditions. So either of these will work, but it will not immediately satisfy those. So just for those of you who studied differential equations, first you try to solve the general equation, right? And then you have some initial or boundary conditions, and you get a specific solution. Okay? So the general solution that we should look at is going to be a times 1 to the pi equals a times 1 to the I plus b times q over p to the I if p not equal q. That's, I don't want to spend a whole lecture on difference equations, but it's not just for this example. In general, when you have difference equations like this, what would happen is you'll get a polynomial, you'll find the roots. Now, if all the roots are distinct, that is, you don't have repeated roots, then the general solution you should try is just a linear combination of, so here we used x to the I, so one solution would then to try is 1 to the I, which of course is just 1. And the other one is the other root to the I. So we would just add, if I had n roots, I would just add up a linear combination of those roots to powers. It gets more complicated if you have multiplicity, repeated roots. But we don't have to worry about that yet. So right now I'm assuming p is not equal to q, so then we don't have a repeated root here. Okay? Now we're almost done with this calculation. So actually I'll just write the answer here. So what that gives us, if we now plug in p0 equals 0 and pn equals 1, well, p0 equals 0 you can just do in your head because then it's just, I'm going to get rid of this ith power here. 1 to the I is 1. Plug in p0 equals 0, that's just a plus b. So in other words, b equals minus a. So p0 equals 0 implies b equals minus a, and if we plug in the other condition we know, pn equals 1, plug in pn equals 1, then that says 1 equals a, factor out the a, 1 minus q over p to the n. Right? So So A is 1 over 1 minus Q over P to the n. So then we have the answer. The answer is that Pi equals 1 minus Q over P to the I over 1 minus Q over P to the n, as long as P is not equal to Q. So that's the explicit solution, whereas this is a recursive solution. So that's the case where we would say it's an unfair game, right? Because one player is more likely to win. So, we should also consider what happens if P equals Q. If P equals Q, that means that the game is just one half each time. In that case, there's only one root here, which is 1, and it has multiplicity 2, and the theory of difference equations gets a little bit more complicated. We have to account for that somehow. So I think an easier way to think of it would just be take a limit, okay? Because it should be, let's let x equal Q over P, and let's look at what happens as x goes to 1 in this solution. So we have 1 minus x to the I over 1 minus x to the n. That's of the form 0 over 0, okay? So we can use L'Hopital's rule to do this limit. So that's the limit, x goes to 1. So I'm just going to take the derivative of the numerator, derivative of the denominator, ix to the I minus 1 over n x to the n minus 1. The minuses cancel. Now, the x stuff is just going to 1, so we just have I over n. So I claim that the answer here is I over n. Now, it could be that something very, very shocking happens, and the limit of this solution isn't this solution. Intuitively, it should be true that if you let the game get more and more fair, this is the unfair game solution. The unfair game solution should converge to the fair solution if the game converges to fair. So I would find it very, very surprising if this were not true, but that's not a proof. Okay? But to prove it, all you have to do is just plug this back in and check that it works, and if you plug it in, you'll see that it does work. So in fact, it is that way. It's not some amazing thing where it suddenly becomes, discontinuity. That's a much easier solution, by the way. This thing looks kind of complicated, and this is very simple, just I over n. So I don't expect you to memorize the result of the gambler's ruin. The important thing is the thinking conditionally and recognizing the structure of the problem. But I did want to mention a few, just to kind of have, what's the moral of the story. Well, aside from the fact they should condition, I computed a few numbers that, for specific cases, what happens. So first of all, the I over n is fairly easy to remember intuitively because it's saying that the probability, in the fair case, the probability that A wins is proportional, actually just is equal to what fraction of the wealth that A has. So if A starts out with 2/3 of the money, A has a 2/3 chance of winning. So that's easy to remember, and that's pretty neat. And let's see. I did just numerically a few calculations for what happens in the unfair case. So this is the fair case. I think is then pretty intuitive if you think of it the way I just said. But what about the unfair case? So I just plugged in some numbers and did it on a calculator. So let's let, just for example, I equals n minus I, because that's the case where they start out with equal amounts of money. And let's let P equal 0.49. So the game is just very slightly unfair towards gambler A, right? Just only by 0.01 away from being fair. So slightly unfair each round. Okay, and then see what happens. Well, if n equals 20, then the chance that A wins is 40%. So that doesn't sound too bad. If n is 100, so that's the case where each player starts out with $50 and the game is just a tiny bit unfavorable to player A, then it's only a 12% chance that A wins. And if n equals 200, then 2% chance. So if they each start out with $100 then there's a 98% chance that B will end up with all the money, even when it's just unfavorable just by this tiny 0.01 amount. That's in the case where the two players start out with equal amounts of money. Okay? Now, if you think of what's the interpretation of this in Las Vegas, well, it's almost always true that the casino or the house has more money than you. That's true for almost everyone. So on the one hand, it's very unfair in this direction in terms of fraction of the initial wealth, whereas this is the case where it's completely, you start out with the same amount of money as the casino. And secondly, the games range from slightly unfair to very unfair to the gambler, all right? So we're also in this case, so that's really why it's called the gambler's ruin. If because that says, basically, if you go and keep gambling over and over again, you'll lose all your money with high probability. So that's what it's saying. Okay, oh, and there's one other subtle issue that I wanted to mention with this, which is, what about the case, have we ruled out the case that the game oscillates forever? And it doesn't seem like we have, but actually we have. So consider, what if I asked the same question, except I asked for player B instead? That is, I said, what if I said, what's the probability that B wins? What's the probability that B wins and A is ruined? Okay? Well, we're not really going to go through this entire thing again, right? It's just like, all we did was change the name of player A to B and change the name of B to A. We can immediately write down the answer. Okay? So from this, we can immediately write down the probability that B wins and A is ruined. Now, if you do that, and if you add those two numbers, let's just do it quickly for this case. If we did the same thing for B, we would get n minus I over n, because n minus I was how much B started with. If we add, so I'm just going to mention this for the fair case, but the same thing happens in the unfair case. If we add I over n plus n minus I over n, we get 1. So for the fair case, this is the probability that A wins and B is bankrupt, and this is the probability the other way around. Those add up to 1. That means there's no probability left over for oscillation. So this tells us that the probability is 0 that the game goes on forever. Mathematically, there's nothing in the equations that says the game can't go on forever, right? But probabilistically and statistically, it has probability 0, so it would never actually happen. Probability 0 of game going on forever. So we didn't have to do a separate calculation of what's the probability that the game ends, because the probability that A wins plus the probability that B wins is 1. There's nothing left over. All right. So that's the gambler's ruin problem. Now, so spend the rest of today starting random variables, and we'll just be continuing lots and lots and lots of random variable stuff. So why do we need random variables? Well, you can already start to see that the notation starts to get kind of unwieldy when we're talking about this problem. Like, so far, probability is always, everything's defined in terms of events. And so we made up a lot of notation, like let A be this event and B be this event. And so what if we wanted to say, what's the event that player A starts with I dollars, or what's the event that player A has I dollars at time 7? We can make up some notation for that. And we say, well, what if we want one player to have this amount and one player to have that amount, and another player has some other amount, and what if we want to say that the total or certain differences or whatever are certain values? We'd very quickly run out of notation, right? So it's unwieldy. In math, we're used to thinking about numbers and variables, right? Okay, so we need this concept of a random variable, but it's actually pretty subtle how to define it. So what is a random variable? And the first time that I ever learned random variables, I didn't really learn it because the definition was something like a random variable is a variable which takes random values. That tells us nothing. And I've actually been tracking the definition of random variable on Wikipedia for the last few years, And in the early years, when I first started looking at it, that was basically the definition. I wrote it down somewhere. A random variable, this used to be the definition, on Wikipedia. A random variable is defined as a quantity whose values are random and to which a probability distribution is assigned. That's what it used to be. So they did say this mysterious word distribution, but that doesn't tell you what it is, right? I just like assign a distribution. Well, you haven't said what a distribution is, but even saying that the definition is that you're assigning a distribution doesn't make sense, right? Because you say, here's this random variable. If we assume we know what a distribution is, we can assign it, but what does that have to do with what is a random variable? Okay, so they still, I looked at it this morning, they still had something kind of vague like that as the first sentence, and then the second sentence was basically like, it's a function which is from somewhere to somewhere, which is measurable, and so the second part so the first part is kind of supposed to be an intuitive definition, but actually doesn't give you any of the intuition. And then the second part of the definition is mathematically formally correct, but you can't really understand it unless you've had measure theory and real analysis, and anyway, it still doesn't give you any intuition. Okay, so we need to think carefully about this question, and we're going to start on it today, but we're going to continue. Actually, before we even get to what is a random variable, I should ask, what is a variable? Now, we've all been doing algebra and calculus and stuff for years, and we use variables all the time. We don't usually talk about what it means, right? Can anyone here define the word variable? Either intuitively or formally. We use them all the time, right? So somehow we sort of know what it is, but sort of maybe we don't. Anyone want to attempt that? Yes?
It's an abstraction of a quantity that can take different values.
Okay. So he said it's an abstraction of a quantity that can take different values. And that is sort of a very good intuitive description of what we're thinking. But now let's try to push that a little bit and see what does that actually mean. So, we usually use variables. We have like an equation, x plus 2 equals 9, and then we usually say x is a variable, right? And we're going to solve this equation, and then we solve it, and we get x equals 7. Now, 7's a constant, not a variable. So you said, it can take different values, but it just never has ever happened that 7 has changed into something else, right? It's a constant, not a variable. Now, maybe I could have written down an equation with 2 solutions rather than 1. You say x is a variable because it could equal 5 or equal 7. But nevertheless, it's either equal to 5 or it's equal to 7. It's not somehow both. Okay, so it's kind of a mysterious concept. Now you can say x is a variable. That means we allow it to it's just a symbol, and we allow that symbol to stand for different possible numbers, different possible constants, which is true, but then x itself, it's easy to confuse the symbol x with what it stands for. X is just a symbol that's standing for a number, but there's no such thing as a variable number. So again, what does it actually mean? Well, I think philosophers disagree on that question. But from my point of view, x here is actually, it's a symbol that stands for a constant. It's not really a variable. And as soon as we want to actually, my opinion on this, is as soon as we actually really want to make precise this thing of like things changing over time, we need the notion of a function, right? So, because if you have a function, then you can imagine the graph of the function, and that's showing something changing over time. But just with an equation like this, we can't actually get variables. Now let's come to the random variable case. What's a random variable? Well, random variable, it's meaningless to say it's a variable. Actually, what it is a function, okay? And so the deepest thing, or one important thing to understand about this is, where does the randomness come from? Because we're going to define a random variable as a function, and functions are deterministic, and this is supposed to be random, so where does the randomness come from? So the definition is that it is a function from the sample space which we've been calling S. That is, we have some random experiment to the real line. So as input, we have this sample space, and we've been drawing these Venn diagrams. The input is some possible outcome. Little s is some, we have an experiment that has different possible outcomes. Little s is one specific outcome, okay? And that gets mapped to, here's the real line, and often we'll call our random variables x, but there's no rule that says we have to do that. But that's sort of the default choice if we're dealing with one random variable. So it's a function from the sample space to the real line, but it takes some time to think about what does that really mean, and how can you reconcile, this is the mathematical definition, to try to reconcile this with this vague intuition that's supposed to be a random quantity, right? So that's something we'll talk a lot about, but the sooner you start thinking about this, the better. So the idea is that we should think of a random variable as just as a numerical summary, and summary is interpreted very broadly. I'll put that in quotes. It's just it doesn't have to be summarizing the entire it doesn't have to be summarizing the entire experiment. It says that it's summarizing some aspect of the experiment. So I'll just say of an aspect of the experiment. And so to answer the question I asked about where does the randomness come from, the randomness comes from the experiment, because we're assuming we have a random experiment. Remember, we assigned different probabilities to different possible outcomes, right? And the probability of the entire sample space is 1, right? And different events have different probabilities, okay? So the randomness comes from the random experiment. After we've done the experiment, we observe a specific outcome, let's say little s, that is after we've done the experiment, and we see, oh, the outcome of the experiment was little s, okay? Then we map that to a real number. And the gain from doing that is just real numbers, is just something we're comfortable, friendly things to deal with, right? Whereas s itself could be something very abstract, and we're just mapping it to just a number. So each possible, there are many s's here, many dots, maybe infinitely many. Each possible outcome gets mapped to some number. Okay, so it's a very, very general, useful framework. So let's do a couple simple examples, and then we'll be doing lots more examples, basically for the entire semester. But just to start with a couple simple and important ones. Let's start with the simplest example, other than a constant. I mean, we could say, well, just let everything equal 7. But technically, that's a random variable, but that would not be an interesting one at all. That's just a constant. Okay? So if we want one that's not a constant, then the simplest thing we could think of would be 2 possible values. So we may as well say those are 0 and 1. So this is the definition of the Bernoulli distribution. And I'll have to define the word distribution. And we'll be talking a lot about distributions. But for right now, we're talking about random variables. And I'll tell you later what the distribution means. Bernoulli, so a random variable x is said to have the Bernoulli distribution. Right now, just think of that as the definition of the word Bernoulli, the term Bernoulli distribution. And often I abbreviate Bernoulli to Bern. If x has 2 possible values, only 2 possible values, 0 and 1, and let's say, I'm going to call this Bern of P, Bernoulli P. If the probability that x equals 1 equals P, and the probability that x equals 0 equals 1 minus P. So what that means is, we have whatever experiment we have, but suppose that no matter what the outcome is, it's only allowed to map to 0 or 1. There are only 2 possible values. Okay, and suppose that with probability P, we get 1. Probability 0, we get, with probability 1 minus P, we get 0. Okay? Then we say that this is a Bernoulli P random variable. This notation x equals 1, I'll talk more about this next time, but just to say it right now, that's an event. If this were not an event, then it would just be complete gibberish what I wrote, right? Because we can only write p of event. What event is that? Well, intuitively, it's the event that x actually takes the value 1. So it's the event, which is the set of all s such that x of s equals 1. That's the way to write it formally. But intuitively, it's just saying, before we do the experiment, we don't know what x is going to be. After we do the experiment, either it turns out to equal 1 or it turns out to equal 0, right? So that's an event. Okay. Now, so that's called the Bernoulli, and we need to define one more distribution for today. Then we'll be seeing a lot more. So here's the binomial, which some of you have seen before, but I'm not assuming you've seen it. Binomial NP. Okay. So the distribution of the number of successes, I have to tell you what a success is. The nice thing is we can define success however we want. That's a useful principle. Distribution of number of successes in n independent Bernoulli p trials. So I'll tell you what that means in case it's not clear from the context. We have n. So now we know what a Bernoulli is. That we think of this as just doing one experiment, and we either get 1 and think of 1 as success, 0 as failure, right? Now imagine that we do n of those. So the simplest example to think about is flip a coin n times. Okay, but you can think of any example you want where you have n different trials independently, and each one either it's success or failure, not both. Okay, so those are called Bernoulli trials. You can think of lots and lots of examples where that would apply. The distribution of the number of successes in n independent Bernoulli trials is called the binomial NP. And its distribution is given by, to specify a distribution just means, I'll define distribution more precisely next time, but intuitively we have a random variable. The distribution is just kind of like the blueprint that's saying what's the probability that the random variable will do this, what's the probability that it will do that. It's just a specification of the probabilities associated with that random variable. So for the binomial, let's call it x. We want to say what's the probability that x equals k, right? If we've specified that, then we would say we've specified the distribution. So let's call x the number of successes. So we have n trials. So x is going to be an integer between 0 and n, right? If you succeed every time, then it would equal n, and so on. It's just how many successes out of the n trials. We want to find the probability that x equals k. Okay, well, we don't have much time, but luckily this is a very easy calculation. Why is this so easy? Well, just draw a little example for yourself. I'll draw one for myself. So x equals k. So I'm imagining these n trials, and suppose that n is 7, just to have a little picture. Here's n is 7, and k equals 3. So I just said, I'm thinking 1 is success, 0 is failure. So I just said success, 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 and then 4 failures in a row. That would be one way that this could happen. Okay? And this would have probability p cubed 1 minus p to the 4th, right? In general, it's p to the k, 1 minus p to the n minus k. That's the case where we have k successes and then n minus k failures. But of course, any permutation of this would be just as good. So this goes back to counting, right? How many ways are there to rearrange this? Well, we know immediately from the stuff we did on counting that's n choose k, because we just choose where the successes are. So we have n choose k, p to the k. This is called the PMF. PMF stands for probability mass function. And we'll talk more about these, but all it means is that this is just specifying what's the probability that it equals 0 This is for k between 0 and n, an integer. All it's saying is what's the probability that x is 0, what's the probability that x is 1, and so on. Okay? And one more quick comment about the binomial. Suppose that x is binomial NP, and this is we use a tilde to mean that this notation just means that x is the number of successes from n Bernoulli trials. And suppose that y is binomial NP, and they're independent. That is, we'll talk more later about what does it mean for two random variables to be independent formally, but intuitively it just means that the events for x are completely independent of the events for y. Then x plus y is binomial n plus mp. And the proof, you could try to prove it, and we'll talk more about this later. How would you prove it in terms of these equations? That would be kind of tedious. But all of you can just prove this for yourself in your head in just a few seconds just by thinking about what this means. Okay? The proof is just consider n Bernoulli trials and then m more trials. All independent trials. Okay? These are Bernoulli p trials, these are Bernoulli p trials. X is the number of successes in the first n trials. Y is the number of successes in the remaining m trials. So just count the number of successes, total number of successes, that's x plus y. Therefore, by definition, that's binomial. So we can prove this immediately without any equations at all. Later, we'll talk more about the equation. All right, so that's all for today.